All right, you guys, so the two that you actually need to know for the test are these two right here, which we've done a lot of. Arithmetic sequence, geometric sequence. So an example of an arithmetic sequence would be like 1, 3, 5, 7, right? And so it's a sequence because there are commas. It's like a list of numbers. And so a series means sum. There would be plus signs in between. All right, and geometric sequence would be like 2, 4, 8, 16, right? We're timesing by 2. Again, there's commas, so it is a sequence. We also learned these two formulas already, but they're not on the test tomorrow. So these two formulas are for when we're doing a sum. So if it's called a series, there should be plus signs in between, and this is when there's an end number. So for this one, the arithmetic, it's like, I want to find the sum of like the first number all the way to the 100th number, right? So we have an ending number. So these are called finite series when there's an end number. All right, same with geometric. Maybe we're finding the sum of the first term to the 100th term, whatever it is. This is the new one that we're doing today, infinite geometric series. So it's still a sum, and we can only find the sum of certain infinite series. For example, if I added these numbers up and it was infinite, it kept going forever and ever and ever, would there be a sum to these numbers? No, because it would be like infinity and infinity. It's just, we keep getting bigger and bigger and bigger. Same with this one, okay? There would not be a sum. So we'll talk about when there is one. First, we have to learn what sigma notation is. All right, so we've got this list of numbers, and this is definitely a series because there's plus signs in the middle. It is also finite because it doesn't keep going. It doesn't have a dot, dot, dot. There's only 4 numbers, right? This would actually be really easy to just plug into our calculator and find the sum. And the next thing we want to know is this arithmetic or geometric? Yeah, I agree. It is arithmetic because we have a common difference. What's our common difference? 4. All right, so we're going to learn this Riemann sum. Have you guys ever seen that before? Yeah, it's like a funky E. Okay. And on the bottom is what number we're starting on. So we start with the first term. N equals 1. That means that this is the first term. And then I have my second term, my third term, and I go up to my 4th term. So I'm going to put a 4 at the top. That just means I'm adding from the first term to the 4th term in this series. And all we do after that is we use our formula for an arithmetic sequence. So we go back up to this formula right here, and we plug in what this arithmetic sequence is. So in this sequence of numbers, what's a sub 1? 1. And we just said our common difference is 4 times n minus 1. You can leave it like that. So let's make sure this works. If I plug in 1, I get 0, 4 times 0 is 0, and what do I get for my first term? 1. If I plug in the next number, because I'd have to do every number between 1 and 4. If I plug in 2, what's 2 minus 1? Times 4 plus 1? Awesome. What's going to happen when I plug in 3? I'm going to get 9. And when I plug in 4, I better get 13. And it means we add those up. Okay? That's all it means. So the next one we want to look at, is it arithmetic or geometric? Are we adding or subtracting the same number here every time? What are we subtracting? So my common difference is negative 3. So I'm going to start with my Riemann sum. And we're starting with the first number all the way up to how many numbers do I have here? 4, 5, 6. Good. So I'm going up to the 6th term. So from 1 to the 6th term. And we're going to use this formula again for arithmetic series or sequence. And what's A1? It is 1. plus my common difference. I like to put that d at the end. I'm going to put it at the end. So times n minus 1 and then plug in my common difference. But if you put it here before the parentheses, that's the same thing. All right? And you could leave that. And you could check it. You could plug in a 1 and you should get a 1. And you could plug in a 2 and you should get negative 2. And you could plug in a 3 and you get negative 5. And that means you add up all those numbers. Okay? All right, this next one, is it arithmetic or geometric? I agree with you. Geometric. So that means we have a common ratio. What's my common ratio that we're multiplying by every time? Good. So Riemann sum, we start on our first term and we end with, how many terms are there right here? 2, 3, 4, 5, 6. I agree, 7. So we're using a different formula, though. We're not using the arithmetic formula. We're using the geometric formula for a sequence. So it's a1 times r to the n minus 1. What is a1? 1. What is r? 2 to the n minus 1. Okay, again, how could I check it? I could plug in 1 and I better get 1. I could plug in 2 and I better get 2. I could plug in 3 and I better get 4. I can plug in 4 and I get 8, etc., all the way up to the 7th number. And again, you could check just checking the first and the last number and making sure those are right. All right, so another Riemann sum. N equals 1. And this one has how many terms? 3. Arithmetic or geometric? Geometric. And so my R value, what am I multiplying by? Negative 3. So my first term is 2, my R value is negative 3, and it's always to the n minus 1. Okay, and last one, n equals 1. And this one has 1, 2, 3, 4, 5 terms. Is this arithmetic or geometric? What are we multiplying by every time? 1/2. Good. Harrison. N is the term number you're on, so it always starts at, this is the first term, and I'm adding up each term. So you plug in all those and add them up. All right, so then I have a sub 1 is 1/2. My R value is also 1/2 to the n minus 1. Now, every once in a while, they might start at 0, and you have to understand what that means. So, like, let's rewrite this one as if we started at 0. In other words, they're going to say this is my 0 term, my first term, my second term. So what would my n number be up here? 2, okay? And then I'd start at 2 still. That's still my first term. My common ratio is still 2, or still negative 3. But now, instead of n minus 1, I just moved down one number. But let's think about this. If I plug in 0 right here, what do I get? 2. So do I need to subtract anything from my n value? No. And then if I plug in 1, I get negative 3 to the first times 2, which is negative 6. That would give me the second term, or in this case, the first term, because I switched it back a space. Okay, so if you go back 1, which what I did here, I'm actually adding 1 to the exponent. That way it's on the same term. So sometimes they start at 0. So for example, let's say this one started at 0 instead of 1. What's my end one going to be now? 6. And then I have 1, 2, and now I would just have it as an n instead of an n minus 1. Okay? Sometimes they'll give it to you like this. So if they gave you a problem, let's just say it was 5n plus 2. They might give it to you like this. How do I find the sum of the numbers from 0 to 3? Well, I got to plug in 0. What do I get when I plug in 0? 2. Plus, what do I get when I plug in 1? 7. Plus, what do I get when I plug in 2? 12. Plus, what do I get when I plug in 3? 17. And then I would add those up and get my answer. So sometimes they'll give it to you the other way around. You don't have to write the formula. You actually find the sum. How did I know to stop at 3? Because that's my n number. And start at 0? Because that's what they gave me down here. Okay? All right. if there are infinitely many terms, will there be a finite sum? Sometimes yes, sometimes no. So does this one have a sum? 2, 5, 8, 11. If I just keep adding those numbers that are getting bigger and bigger and bigger, is there a sum? No. It's like infinite. It just keeps going. It's never going to stop. Okay, this next one is geometric. This one was arithmetic. This one's geometric. I still am adding 2, 4, 8, 16, 32, 64. Same thing. Does this one have a sum? No, it's like getting bigger and bigger and bigger. There's no way. Okay? So here's one that is actually interesting. I'm adding 1/2, 1/4, 1/8, 1/16, 1/32. Let's look at this square right here. This area represents what fraction of the square? 1/2. This area represents what fraction of the square? 1/4. 1/8. 1/16. 1/32, etc. What is the area of this square? Weird. If I added up all those fractions, what do I get? 1. Does this have a sum? Yes. Finally, the actual lesson. Right here. This formula right here. S sub n, this is for an infinite geometric series, so it has to be geometric, and it's adding forever and ever and ever, okay? That is going on and on and on. So it's geometric. I can tell by this formula. I can also tell because I'm multiplying by 1/2 every time. R is 1/2. What makes it so it has a sum? You might want to write this down. If it's geometric and your R value is in between -1 and +1, it will have a sum. Okay, it's fractions, meaning it's getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. So we will have a sum. And we're going to plug it into our new formula, S sub n equals A1 over 1 minus R. It's a really easy formula. So this is now S sub infinity. We're going forever. We're adding these forever and ever. What's the first term of this geometric series? 1/2. Okay, so I'm going to plug in a 1/2 for A1. Over 1 minus R. And what is our R value in this problem? It is 1/2. Okay, there's a faster way to do these, and it's multiplying by the denominator. I promise it's faster, so just multiply by 2 over 2. And then this gives me 1 in the top. Distribute down here, and it gives me 2 minus 1, which is 1. Which we got by looking at that lovely square. Write in sigma notation and find the sum. Let's just find the sum, because we just did a bunch of writing in sigma notation, okay? So let's find the sum of the series. First of all, does it have a sum? What are we multiplying by every time right here? Yep, R is 1/4. I'm dividing by 4, or R is 1/4. Is this between -1 and 1? Yes. So that means we can use our new formula. A1 is what? Good, over 1 minus R. Instead of actually doing the fractions, you guys, multiply the top and bottom by 4. It's faster. So in the numerator, we get 20. Distribute the 4 here, and I get 4 minus 1, which is 20/3. So if I keep adding those numbers forever and ever and ever, it will eventually get to 20/3. Okay, find the sum of the series. So for this one, what are we multiplying by every time? -1/3. Good. If it alternates signs, it's a negative. Okay. So again, it's between -1 and 1, so we are good to go with our infinite series formula. A1 is what? 3 over 1 minus R is -1/3. Go ahead and change that to a plus. And again, to make your life easier, multiply the top and bottom by what? 3. It's better. 3 over 3. So I get 9 over 3 plus 1, which is 9/4. Okay, so the next one, it's another infinite geometric series. How do I know it's infinite? It's going from n equals 1 to infinity. That little symbol on the top is infinity right here. It's miniature, but that says infinity. And my r value is 2/3. It says it right here, 2/3. My first term is actually 1. You can't see it, but there's a 1 in front. Okay, so if you can't see your A1, that would be a 1 in the front. So it works because r is between -1 and 1. It's going to get smaller and smaller, so we can find the sum of the infinite geometric series. So let's say 1, it's 1 over 1 minus 2/3. And we'd multiply the top and the bottom by 3. So I get 3 over 3 minus 2, which is 3. All right, this one's starting at 0. That's okay. All right, we're still good to go. I still have an r value of 2/3, so I'm doing s sub infinity. My first term, I actually plug in what number to get my first term? 0. Whatever is in the bottom is what you plug in to get your first term. This one started at 1. This one starts with the 0 term. That is still my first term. So I'm going to plug in a 0 for n. What's 2/3 to the 0 power, though? 1. So I still get 1 for my first term. Over 1 minus 2/3. So same thing. It still gives me 3. Okay? And my next one, again, it starts at 0 and it goes to infinity, so I still am finding an infinite series. But for my first term, plug in 0. So if I plug in 0, I have a 0 plus 2, and so I'm squaring it. So what's my first term? It is 4/9. Good. It's in parentheses, so you're squaring out the negative, and you get 4/9. Over 1 minus r. What is r in this problem? -2/3. This guy right here is r. And we're going to multiply the top and the bottom by 9. So if I multiply the top by 9, we get a 4. The 9 distributes. This becomes a plus. 9 divided by 3 is 3, times by 2 is 6, and we get 4/15. Okay. A ball is dropped from a height of 12 feet and rebounds 2/5 the distance from the ball. How far will the ball fall on the 10th ball? This is a good one because what if, this is on the test tomorrow? So we've done these before. We already know how to do these, right? This is just our formula for like a normal geometric sequence. A1 r to the n minus 1, right? So on the 10th fall, remember if it's the fall, we have to plug in 10 minus 1. If it's the bounce, just plug in 10, okay? So for this one, we've got 12 feet. It's dropped 12 feet on the first fall and rebounds 2/5 of the way. So my r value is 2/5, and we plug in 10, and we do subtract 1 on this one, and we get 0.038 feet. Now, what is the total distance traveled by the ball if we never stop it from bouncing? So we've always got our first fall, our rebound, our next fall, our rebound, our next fall, our rebound. Okay, and it's going to keep going and going and going. So that means we have an infinite geometric series. Why does it work? Because our r value is in between -1 and 1. So we can use our new formula for the sum of the infinite series. Okay, so first let's talk about just the falls. So here's all my falls right here. This is the next fall, and this is the next fall, and the next fall, and the next fall, and it keeps going, right? And so if we're plugging into the formula, what's A1, our first fall? It is 12. over 1 minus our R value, which is 2/5. And so we'd multiply by 5 over 5. And that gives me 60 over 5 minus 2, which is 60 over 3, which is 20 feet. Now the book would have you do a whole nother one for the bounces, but there is a much easier way to do the bounces. Instead of doing another formula, do you guys agree that if I just take this out, this first rebound or first bounce is equal to the second fall, right? So that means that all these bounces are the same as the falls, except for the very first fall. So if I take all the sums of these, all I need to do is take out this very first fall, and that gives me the total sum of the bounces, so just 20 minus 12, and that gives me 8 feet for the total sum of all the bounces. All right, and then it does say the total of all the falls and the bounces, so my final answer is 28 feet. And the last one, a duck, which reminds me of a joke. What do you get when you cross a duck with fireworks? A firecracker. Okay, swims 200 meters in the first minute, and then he swims 80 meters in the next minute, and he's getting kind of tired, so he swims only 32 meters on the next minute, and he continues this forever and ever and ever. Is there a sum? Yes, because eventually he's going to get so slow that he stops, essentially. All right, so this is another sum of a geometric series. Okay, and my first number is 200, and my second number is 80, and my third number is 32, and it keeps going. So what's A1? 200. Over 1 minus, how do we find R? Actually, the other way around. Yeah. 80 over 200, which also should be equal to 32 over 80. So it's this one divided by this one, or this one divided by this one, which happens to reduce to 2/5. All right. Times by 5 over 5. We get 1,000 over 3, which is 333.3 repeating meters. That's how far he, like, so think about, I'm multiplying 200 by some value of R to get 80, and you divide by 200.
Gotcha.
Yeah.